Now. Yeah, who cares? Yeah. That one got a lot of views. There's a lot of views on that one. People I didn't even know were viewing that one, picking apart all my arguments. All right, so snow skier skis down the slope and goes for a jump and, splats in the snow there. So this is our problem. We want to figure out this distance. You're not going to be able to figure out that distance without this velocity. So we're going to get to that velocity by doing, I'm thinking conservation of energy. Is that what you're thinking? See, Lauren, conservation of energy. I'm thinking mgh equals 1/2 mv squared plus mgh. Thoughts?
Did you do mgh equals 1/2 mv squared and do 22 as the height?
Yes, because when I subtract that from both sides, it'll be 22 as the height. So velocity is going to be like 21 meters per second.
Yes.
So we leave that ramp at 50 miles an hour on skis. I've never been snow skiing before, but the thought of being on just 2 planks of wood or fiberglass at 50 miles an hour, I would think would be terrifying, just terrifying. But these are these guys who do the snow jump things. Also, but the snow jump things, whenever I've watched the Olympics, it's not flat ground. It's like a slope afterwards. So those suckers are falling forever. Meh. So now it becomes a quite pedestrian, which means anybody should be able to do it kind of problem. But here's where you made it. Range Vx is going to be that 21 cosine 30 degrees. But you didn't have trouble with this part. You said you couldn't get the time right. So that's probably because you forgot to say that you go down 3 meters.
Negative. Yeah.
Negative, I'm wrong, or negative, yeah, you forgot to do that.
Negative, yeah, I forgot.
I know. That's what everybody forgets to do. I don't know if we can or can't. I know that Lauren's going to be the one who decides this because she wanted number 3.
What's the question?
Are we done with this?
No, yeah, I'm done with it.
So we will scratch it off the list. Number 5. So this is the one that Max wants to see? Oh. Then who wants number 5?
I do want to see number 9.
Okay, but 5 is next. Who wants to see number 5? All right, Sam, whose mass is 66 kilograms, straps on his, skis. I read that totally different. And starts down a 40-meter high, 20-degree frictionless slope. A strong headwind exerts a horizontal force on Sam of 200 newtons as he skis. All righty. You've got a variety of ways you can do this. You could do net force on it. That would work. If you don't want to do net force, you want to do energy. I think energy is probably, it says to use working energy. All right. How about we do the work energy theorem? That seems like the way to go, because there's going to be work done by gravity, and then there's going to be work done by the wind. And that has to equal the change in kinetic energy, because there's no other forces that can do work, right? Yeah. So let's do the gravitational force. It's acting downwards, mg. And he's going to go down this direction. So this angle is going to be 90 minus 20. So it's 70 degrees. So this will be, let's get this the other side, mg times the length of the ramp. We don't have the length of the ramp, so that's going to be h over sine 20. Everybody see where that came from? Times the cosine of 70. But what's funny is the cosine of 70 is the sine of 20, and the sines of 20 cancel, so this just comes out to be mgh. Not a surprise, that's the amount of work done by gravity pulling them down, but still, I wanted to make sure that we see all of the pieces because that's what we do. questions? All right, work done by the wind. The wind is blowing this direction. You know, we can turn on that projector and turn off the lights because you guys in the back can't see anything. Back into the darkness. Hello, darkness, my old friend. Come to be crapped on by you again. All right, keep going. Yes? Excellent. So the force is 200 newtons. I don't know the distance, but I'm pretty sure it's going to be h over sine 20 again. And because it's this distance. And the angle between those two distances is this angle, which has got to be cosine of 90 plus 70, which is 160 degrees. There it is. Problem done. You can plug in all the numbers. Would you like to plug in all the numbers? It'd be kind of fun. No, I mean, not fun at all because I don't care. But for me, it's 66 times 9.8 times 40 over, well, I don't have to do 40 over anything, just 40. Just 40. Plus 200 times 40 over sine 20 times the cosine of 160 degrees equals 1/2 mv squared minus 0. Woo. I don't know who asked, but how's that? Will that do? That'll do. That'll do, Mr. Shelton. That'll do.
Mr. Shelton,
What?
how fast would the wind be going to produce 200 newtons of force?
Interesting question. You guys at home, did you hear that? Would you like me to repeat it? Because it is an interesting question. How fast would the wind have to be going to produce 200 newtons of force? Well, I mean, how do you figure this out? There's a method to do this. Does anybody know what the method is? Because we're learning it right now. And we are being taught it. Yes, sir? Not necessarily this time, although we could do it that way, because you could treat it like you're moving through the wind and feel that as a force. That is a method for doing it. But in this case, there's another method for doing it, because we could treat the wind as a collision. That the air strikes you. And you have to ask yourself, of course, the wind has one velocity, because we're trying to figure out the velocity of the wind. The wind has one velocity before it strikes you and a different velocity after it strikes you. So there is a change in momentum of the wind, which will result, of course, in an impulse. Now, to tease out the force from here, you have to figure out how long it takes for the wind to become stop or have its velocity changed after its encounter with you, which is actually, I'm not sure we have a good answer for that. The problem too is that how many air particles are striking you? So the density of the air is going to play a role in this, because that determines the number of air particles striking you. But there's also something else. The air is spread out. So your cross-sectional area makes a difference, which is why you can tell we're getting back to the whole idea of drag. But we never covered it really, because at the time, it seemed ridiculous to talk about it. But this is actually where you start developing the definition for how drag works. Cross-sectional area plays a big role in there. Your shape determines how long it takes for the air to change velocity. More streamlined, the air doesn't have to change as much of its velocity, and therefore it doesn't take as long either. So you affect both this side and this part. But also, we tend to speak of anything having to do with wind in terms of pressure, not force. And pressure is force over area. So the cross-sectional area also plays a role here. So there's quite a few things that would determine this. But we could probably come up with a pretty fair estimate for how fast the wind's hitting you. But we would need some factors first. So interesting question. And a nice diversion from this boring old physics we're doing. All right, so Next question would be number 6. We're moving right along to number 6. Who asked about number 6? That's Kyle. Kyle. Ever seen one of these, Kyle? Do you even know what this problem's about? Put your mask on your face. I don't want to see your nose. No nose dangling. I won't even hear you. Your voice won't travel unless it goes through the mask. I hear that a lot. Not necessarily just from you. Very seldom from you. I think Kyle thinks he does things wrong. All right, so but you didn't answer my question, which have you ever seen one of these? Who else has lived someplace where they have these? They don't have these in Florida. Yeah. Yeah. They're a lot less cool when you've had to see one in action. I've had to swerve out of the way of an oncoming truck who had to use one of these. So it was a lot less fun under those circumstances. It's like 11 p.m. Truck comes down the mountain and it's only like a 1.5 lane road on the mountain as it is. Oh, because it's like, I mean, the gravel they're talking about here, it's like 2 feet deep.
Really?
Yeah, it's not like they're embedded in it. They have to get a big wrecker to come out. And usually if they don't jackknife, they've usually got lots of damage too. So if they hit one of these, it's bad for the truck. So it is better than falling off a mountain, although they are likely to barrel through cars on their way to get to this, which is just too bad. So can I help you? Just set it right there on my desk, please. I'll make sure she gets it. Thank you.
What is it?
I don't know. And class at home, just so you know, somebody opened my door in the middle of class, walked in and wanted to hand me something. You can't do that. The rules state no.
Yeah, that's weird.
There's no passes, no people walking through the halls to hand me stuff. I don't know what it is. I don't care. I'm going to light it on fire. That guy looks sketchy. And there's no telling where he's been.
I don't want to touch it.
That's yours. I'm going to spit on it now because you brought it into my room. Lauren, come see me about this.
Is it from Mr. Gennaro?
Of course it is.
Yeah, I forgot about that.
So Kyle, we're going to get back to work now, but this is, you people at home, this has been an uncomfortable afternoon. This has been a hard week. I'm looking forward to this week being over. I wish I could get signed out. Can one of you guys just call the office and tell them to sign Mr. Shelton out? I want to get that phone call. Mr. Shelton, yeah, you'd come down to the office. You're being signed out. Okay.
We can do that right now.
No, they'll know it's a stupid joke, and then I'll just get called down to the office to be told I'm in trouble again and stop doing things that might have any resemblance of being fun. So get back to physics, because that's a lot of fucking fun. So, all right. So the truck has kinetic energy here. It has none there. So we're looking at the work done by two things: the frictional force acting on the truck and the work done by gravity acting on the truck. I think, again, I'm going to stick with the work done, or the work energy theorem on this one. Gravity's acting downwards on the truck. So there's an angle of 96 degrees between the force of gravity on the truck and the displacement of the truck. Does that make sense? So I'm looking at probably the work done by gravity being mg for the truck times whatever that distance is. This is what we're trying to actually figure out, is this distance. And the cosine of 96 degrees. That's going to be negative, but that doesn't matter. The next part's going to be the work done by friction. And I don't think I have to spend a lot of time convincing you that the work done by friction is a frictional force of mu mg cosine 6 degrees. Right? We're done with that. We know how that comes about and I don't have to play any games with that. I'm looking all over the room, but apparently this is the only person that needs this is Kyle. But that's not true because I see people at home taking notes, so they must need it too. Now, careful here. This is another cosine of 180 degrees. These two don't represent the same thing. Kieran?
What is the cosine 96 from?
That's the angle between the force of gravity and the displacement of the truck. So that was from here to here. The truck is going up the ramp, but gravity's acting down.
Okay.
Lauren?
I was telling you, I would like this.
Oh, gotcha. That's it. Those are the only two things doing work in the system. So that has to equal the change in kinetic energy. You're solving for D here. So you're going to set these two things equal to the change in kinetic energy. The change in kinetic energy is going to be negative because the final kinetic energy of the truck is 0. The initial kinetic energy of the truck is 1/2 mv squared. So, these are going to produce negative signs. This is how it's done. I can't think of anything else. All the m's cancel out. Although they gave you the mass of the truck, but it's not necessary. Is that all right? Yeah. Although I think they gave the mass of the truck, but you don't need it.
Yeah, they did.
All right. So next question. That was 6. What?
So on the last problem, why do you do the work done by gravity instead of just counting like kinetic energy minus the work done by friction equaling the potential gravitation?
I don't know. Actually, do you want to know why I want to do it this way, Devon? It's real simple. It's when we talk about it the other way, we run into trouble. So tell me, you set up a conservation of energy formula, right? What did it look like? Just give me the 3 letters. Something plus something equals something, or something like that. What was it?
Kinetic energy minus the work done by friction equaling the gravitation.
Okay. Now, I'm already seeing a problem here. And it's subtle. But how'd you calculate the work done by friction? Did you do friction times distance times the cosine of 180 degrees? Because this produces another negative sign. And does that make this negative positive? Exactly, which is 100% wrong. And well, no, I'm not trying to be a jerk. I'm saying the problem is we run into this issue with the strict interpretation of work and what it can do versus the concept of conservation of energy, which is supposed to be tracking where the energy has gone. Our concept of conservation of energy, as I teach it, which may not be correct apparently, is that there is an initial state and there's a final state, right? This is the initial state. Well, I'm sorry, this is the initial state and this is the final state. But the work done by friction occurred over the entire state, right? It was happening the whole time as the truck was being brought to rest. So when we have to figure out how to deal with that, I think it's best to recognize that from the onset, we know that this has to, that this has to be true. We have to know that from the beginning. That there's energy that is missing from this relationship. Therefore, there's more kinetic at the beginning than we're going to have potential at the end because friction played a role in it. If we start off under that premise, then we can skip this part and just consider work as a quantity. How much energy left the system in the form of friction? And then how we deal with that is to ensure that the kinetic energy is greater than the gravitational potential energy. Does that make sense? So what you did by saying kinetic energy minus the work done by friction isn't a problem unless you then go and strictly interpret the direction of the forces acting on the truck and somehow produce a positive sign here, which screws you over. Does that make sense?
Yeah, kind of. I just don't see how you would know that you can't do that from the start, because, like, to me, that looks like you could do that and kind of answer it.
I didn't say you couldn't do it from the start. I'm just saying you have to be aware that, truthfully, in the conservation of energy formula, all values of energy have to be positive. You just need to know where to place them. Meaning, if you're going to deal with conservation of energy, the truck started at the beginning having this amount of kinetic energy and ended by taking that energy and distributing it in two places: gravitational potential and an increase in the internal energy of the road surface. Okay?
Yeah. Trying to figure that out.
I don't have a third way of saying it. But
I can understand 5 seconds. I was really understand.
okay. All right. Or just do it this way, because the work energy theorem always works. All right, let's go to the next one. That's number 7. We're making great progress. No, we're not. Number 7. Really? We have to do this one? Who asked for number 7?
I only want to see part A.
Okay. Number 7. Screw you, thing. All right, so I will do one of these and do one of these and one of those. And there's friction. All right, so it says use work and energy to find an expression for the speed of the blocks in the following figure just before it hits the floor. Hits the floor, H. All right, find an expression for the speed of the block if the coefficient of kinetic friction of the block on the table is mu k. All righty. Right now, under this circumstance, the only thing that has energy is the block that's hanging. Nothing else is moving, and the block on the table isn't going to change height. So in a few moments, there will be a second circumstance where this block will be just about to hit the ground, and this block will be just about to fly off the table. But this block has moved the distance h, and this block has moved the distance h, and now both of the blocks are moving with the same velocity. Correct? So I'm going to do this in the Devon way because I want him to see it. Because Devon wants to see, why can't we use conservation of energy here? And I'm going to say we can. So in the beginning, the box on the table has gravitational potential energy equivalent to mgh. This is the only energy that exists in the system at the beginning. At the end, both blocks have kinetic energy. They're both moving, so I will have to sum their kinetic energy. Block 2, the big one on the table, has moved to the right, but it has not changed its height, so its potential energy never changed. I don't include it. The box that's hanging is now at its lowest point. It has no potential energy, so I don't include it. But the table did get hotter. There is a change in the internal energy of the table. So some of the energy in the system now has turned into heat in the table. How much energy are we talking about? Well, the amount of energy, not direction, the amount of energy is going to be the frictional force times h, which is going to be mu mgh. That's just the amount of energy. Force times distance for the frictional force. So now I take mgh equals 1/2 mv squared plus 1/2 little mv squared plus mu mgh. Solve for v. How's that, Alex? Is that good?
So the box on the top moves the same distance as the box falls. The other box.
We assume the cable doesn't stretch or anything like that. Yeah.
Okay. Thank you.
For the same reason why they also have the same velocity now. All right, next problem. So that's number 8. All righty, number 8. Oh, really? We're going to spring shoot the guy? Yeah, sure we are. There's some people I would like to spring shoot. I think we should create. You all looked at Kyle, didn't you?
5 distinct people looked around. Turned around. The acceleration was like 225.
The acceleration of the guy?
Yeah.
The instantaneous?
It was fast.
That's a lot. Well, the spring is 80,000 newtons per meter, right? And it's compressed 46 centimeters. That's like half a meter. So a quarter of that's 200,000 newtons. Yeah, that's going to hurt when you release that into them. You get just hit. I mean, 2,000 newtons is about 1,000 kilograms of weight. That's 2,000 pounds. So that's getting hit with 2,000 pounds instantaneously in the back when you release that spring. He would die. Yes, he would die. He would be an unfortunate. He'd be folded. He would be like the true human scorpion, you know, where they fold backwards on themselves. A great Reddit, by the way. If you want to look for some fun stuff, look up the subreddit, human scorpion. Human scorpion. Or no, full scorpion. It's basically people who have a spectacular failure and end up trying to do something funny to impress somebody and instead impressed us. And we get the video usually of them, it's like babies falling down a little slope and, bending backwards on their way down. Usually if they're done right, they're filmed in spectacular slow motion. So you can see the moment when their pride breaks. That's my favorite part. So, all right. So spring, person. Oh no, I didn't think it out all the way. All right, the spring shown in the figure is compressed 46 centimeters and used to launch a 100-kilogram person. 100 kilogram, not a good physics student. It says physics student here. No, this would be used to launch like a really good social studies student because a physics student would understand not to do this. This is like a Darwin Award right here. Go ahead. Anybody who thinks this is a good idea, enjoy. Used to launch a 100-kilogram physics student. The track is frictionless until it starts up the incline. The student's coefficient of kinetic friction is 0.12 when it hits the incline. And what is the student's speed just after losing contact with the spring? That one's just 1/2 kx squared equals 1/2 mv squared. Not a whole lot to do there, so I don't think I had to spell that one out. That's part A. Keep going, because I don't know who asked this question. All right, so part B. How far up the incline does the student go? All right, well, this is still the amount of energy we have, so I'm sticking with that. And when it says how far up the incline does they go, do they mean this or do they mean this? So I don't know the answer to that. And it's not clear.
Yeah, they don't make it clear at all.
So probably some of you found the height. I'm going to find this, I guess. And if it's wrong, then divide by the sine of 30 and get the other. All right. So here we go. This is how much energy we have. And we want their maximum displacement along the incline, which means that we're looking at a point where their kinetic energy is going to be 0. So they're going to reach some point over here, and their kinetic energy is going to be 0. We can do this as work energy, or we can do this as conservation of energy. I don't know who asked, so you pick. All right, so if we do conservation of energy, there's going to be the elastic potential energy, which is the initial energy of the system. And, whoops, I need to take into account the fact that the person is also going to be changing height before they reach the slope. So I'm going to choose the bottom of the slope as the 0 for the problem, because I don't know how high up the slope they go. So it makes sense to make my reference point, down here. So ish. All right, so whatever that is. And that's going to have to equal, they're also going to have gravitational potential energy here, and they've stopped, but they're also going to have left, well, if it's friction, they might be leaving a big human stripe of themselves along the length of the hill. So we'll say that there's a little internal energy that is now spread out all over the slope portion of the area-ish. So we want to know how far they go. And this height is related to this length. So let's put it all in terms of the length. So this part's going to be, the 1/2 kx squared plus the mgh for our starting height. That's going to equal mg s over sine 30, right? Because that's the height. Plus the work done by friction will be the frictional force, which is going to be mu mg cosine 30 degrees. That's just the frictional force times s. Solve for s. I'm done. Are we good? Okay. It could shoot you across. But finding out if it does or not, a little harder than what we've done in the past, because we don't know where they would leave. If we assume a consistent radius of this part of the hill, we would have to find the point. This would be the sphere problem, by the way. It would be exactly the same as the sphere problem. And you can treat it as the sphere problem with a little extra energy at the beginning. And you could find out if they do indeed leave contact with the ground and become a projectile for part of it, which could also be fun. All right. So not only do they have a broken back, but now they're sailing through the air, about to plant themselves on their face. Yep, human scorpion again. All right, so good enough with that one, or is there more? Oh, you've been waiting desperately for number 9. 3 minutes left. God. That's okay. I did 10 and 12 on the other class. Number 9. Oh, okay. You need to know one thing, and then you can do all of it. That
Teacher, please pardon this interruption. The winner of the teacher gift card raffle for this hour is Mr. Schwartz.
why is he going to freak out? Oh. Fun.
Yeah, no. Oh, it's Nick. Yeah. I'm
Well,
wondering, like, all my signs are wrong.
You got it wrong? Let's just make sure that, I mean, you would do your calculus right. So all of that? Chain rule, right? Did you forget the chain rule? Or did you bring an X out with the chain rule like some people do?
I did that.
All right, so before you guys like devolve into like what you do when you're think it's the end, this comes directly from the definition of work. If you pull this integral, that means we're talking about a small amount of work equals a small amount of displacement. You divide both sides by dx, and we get dw dx equals F. But when you do work against a conservative force, you store that work as potential energy. But the work is done in the opposite direction of the force. So the force opposes the change in potential energy. So potential energy increases when you're moving upwards. The force that causes it must be pulling downwards. All right. So is that good enough for number 9?
Yeah.
We did number 10 in class. We did. Who asked for 10? I did a whole big thing with the thing and the hold'em and the stuff. I am happy to do that one again, but it hurts me in the heart. We did 9, so we're doing 10 now. And you said the bell rings like in a second, so it's like. Well, I don't know that was any fun for me, but I hope it was no fun for you too.